It gives you the height that you dropped it from and the height that you're dropping it to. What the heck just happened there? All right, so let's try that again. Draw there. So this is modeled right after a question that was on the actual exam. It doesn't have the explanation portion of it. It's just the math portion, but you can imagine there's probably an explanation portion to follow along with it. So what's the starting height? 2 meters, and then it bounces up to what?
1.5 meters.
All right, so it starts 2 meters above and hits the ground and then bounces up to 1.5 meters. So I'm not sure if you understand what they're getting at here, but you need to. This problem combines more than one thing together. You either have to use kinematics or conservation of energy, but what you need is how fast is the ball going just before it hits the ground, and then how fast is the ball going right when it leaves the ground. Momentum is all about velocity. The heights are a distractor, and you need to see through that to understand the heights are here to give you something to use to figure out the velocity. That's the first thing. Now, if you want this homework session to be helpful, you should write that down if you didn't know where to start, because that's the most important detail. I'm gonna be honest, this is the kind of stuff that's on your test. I'm gonna do this. So this is the final velocity after it leaves the ground. This is the initial velocity just before it strikes the ground. So I'm going to use conservation of energy because it's faster, but you could use motion equations, that would work too. So I'm going to say that it had gravitational potential energy when it was released and kinetic energy right as it hits the ground. So I'll say that mgh is equal to 1/2 mv initial squared. So conservation of energy is used just before it reaches the ground. M's cancel. So in this part, you won't need the mass. You'll need it in a minute, but in this part, you don't need the mass. We just need to figure out the velocity. So the initial velocity is going to be the square root of 2gh. Now, I don't really think I have to redo that whole problem to understand that it's going to leave the ground with kinetic energy, and its maximum height will be when all that energy is gravitational potential. So 1/2 mv final squared is also going to equal mgh. So v final is going to equal the square root of 2gh. The right side, the height is 1.5 meters. The left side, the height is 2 meters. So this one is the square root of 2 times 10 times 2. And the right side, square root is 2 times 10 times 1.5. Now, I'm going to let you in on a little secret. Your homework was already submitted, right? It's due today. If you think writing down the right answer is what I want to see, you're wrong. Because I know who turned it in on time. To me, anybody who turns the homework in after today has all the answers because we do them in class. There'll be a video recording of all the answers. Turning in the right answers, which a lot of you do after the due date, isn't what I'm looking for. You want to impress me? Write the notes down that tell you how to solve the problem. That tells me that this was a meaningful time for you. You have something to study from. Because you're going to submit it, but I'm not a fool. I look at the homework as it gets submitted, and Canvas makes it easy for me to know when it got turned in late. So what I want you to understand is if you're turning it in late, that's something I look for. I give you guys credit because you need it for your grade. But this quarter, I want to see that if you're turning it in late, it's because you used this time wisely and wrote things down to help you. Still not interested in giving you full credit. I think that that's wrong. You should turn in what you did. But getting the right answer now is kind of ridiculous. You should be writing down what you did wrong. And if you didn't do the homework, you should be writing notes down. Because look, you're going to have your test on Tuesday. You're going to know who can do this stuff. So perfect homework and failing test, they go together kind of funny, don't they? So I'm trying to impress upon you that there's no way to escape this. You're not impressing me with a perfect homework assignment. I want this to be a learning experience. So that goes here for the initial velocity, and that goes here for the final velocity. But they asked for impulse. Impulse is still either change in momentum or force times time. There's no way to get the force from this. But there was a way to get the change in momentum for this. So that's what you're really doing. MV final minus MV initial. And even now, some of you should have numbers here if you didn't before. Even now you're going to get it wrong because you're not thinking the way you need to for a problem like this. Momentum is a vector. You need to pick one of these directions for the velocity to be positive and one to be negative. These are both plus or minus. You have to select what you know about the problem. So pick which way is positive. Is up positive or is down positive? If up is positive, then when you do final minus initial, your initial velocity needs to be negative, right? It was going downwards when it hit the ground. It was going upwards when it left the ground. So you need to make this value positive and this value negative. There's a larger impulse because it stopped the ball, turned it around, and sent it back. That's why that, you're going to get that double negative sign right here. I know it's subtle. Each one of these things is a point though, right? Now, I don't know what the rest of the problem is about. I have not done the numerical part, but we've really done most of the math. Do you need me to do any more? I can't hear you. Could you try again?
I'm still confused by where you get the mass.
Where I get the mass? Don't they tell you the mass of the tennis ball? Then I guess Google. Oh, I say it in an earlier problem? Oh, okay. Then do use that mass of tennis ball. I thought I gave a mass of a tennis ball somewhere in the homework. Okay. All right. So yeah, use 58.5 grams. Is there anything about how long it's in contact with the ground? So you have to find the force, or is this the extent of the problem? All right. So once you get this, there is another step then, and that is to find the force. They tell you it's in the ground for 4 milliseconds. So that's 0.04 seconds. You do have to convert that to seconds. You can't leave it as 4 milliseconds. That's because everything over here is in kilograms meters per second. So you'll need your time to be in seconds to get a value that's in newtons. Also, you'll probably have to put the mass in kilograms if you want this to come out to be newtons. I think that's probably enough talky about this problem. Yes, sir? No. No. If it asks for impulse, the mass is required because it's mv minus mv. So it won't cancel out when you go for the force because a larger ball would require more force because it has more inertia. Impulse is connected to inertia, so the mass is going to be required if you're asked for it. There's certainly times where the mass cancels out when we're like finding a velocity or something like that. But in the case of impulse, the mass will be required. Yeah. Move on to another one? Mm-hmm. Yes, Leo. Yeah? Sorry, I could pull up a copy. I didn't.
A 0.5 kg sphere traveling at 2 meters per second provides velocity with a 1.5 kg sphere at rest. What is the velocity of each
So an elastic collision question. So how fast and what size is the first sphere?
0.5 kg.
Okay, so the mass is 0.5 kilograms and 2 meters per second. And the other one is how heavy? 1.5 kilograms. And that there's a collision, yay, boom, pow. And then we don't know what's happening after, but their mass stays the same. We just have two velocities. An elastic collision is pretty prescriptive. What I mean by that is you should know what to do. There's a prescription here. There's a set of directions. If it says elastic, and it does, then the momentum is conserved and the kinetic energy is conserved. You must generate two relationships. So I'm going to start with a momentum relationship first. I'll have the momentum of the first ball plus 0, because the second ball has no momentum. And that has to equal the momentum of the first ball plus the momentum of the second ball. So that will be 0.5 times 2 plus 1.5 times 0. And that has to equal 0.5 times V1 plus 1.5 times V2. You can't solve that. There's one equation and two unknowns. You need more information. So kinetic energy is next. The kinetic energy of the first ball plus 0, because it's not moving, will have to equal the kinetic energy of the first ball plus the kinetic energy of the second ball after the collision. Now, for momentum, it's not clear, but I have made this direction the positive direction, because I made the one velocity we're given positive 2. I want to tuck that away, because if my answers come out to be negative, that means that after the collision, one bounced backwards. That's possible here. One of the balls is lighter than the other. So it is possible it'll ricochet off and bounce backwards. So 1/2 times 0.5 times 2 squared has to equal 1/2 times 0.5 times V1 squared plus 1/2 times 1.5 times V2 squared. I'm going to get rid of the 1/2s real quick, because I don't want to do 1/2 of 1.5 and stuff like that. And actually, I'm thinking about dividing by 0.5. Because it is, just between us real quick, a little aside, we did all the physics. The physics is done. You have two equations and two unknowns. We're talking about algebra 1. I feel like this part you can do, you don't need my help. Now, I know better. I'm going to help you. But once you generate that, you've done all the physics. There's no more physics to do. The only thing that's going to be left is interpreting the results. That might be a little physics. But I'm just looking for easy ways to deal with these two equations. So let's write them a little neater. I'll have 0.5 times 2, that's just 1, equals 0.5 V1 plus 1.5 V2. And 0.5 times 2 squared is 2, equals 0.5 V1 squared plus 1.5 V2 squared. There, I'm just cleaning it up. Now, you might not see why I want to do this, but I'm going to divide by 0.5, because 1.5 divided by 0.5 is just 3. That's a lot easier to work with. So I'm going to do that. 1 divided by 0.5 is 2, and that equals V1 plus 3 V2. Those numbers are just easier to work with mathematically. You guys understand why I'm doing that? All right, good. So I'm going to do it on the other side too. So 2 divided by 0.5 is 4. And that equals V1 squared plus 3 V2 squared. That just looks easier. to me. I like the integers. I'm going to solve for V1. V1 equals 2 minus 3 V2. And then I can take that and plug it in here. Substitution. Good old-fashioned substitution, algebra 1. 4 equals 2 minus 3 V2 quantity squared plus 3 V2 squared. Now, again, this is just boring as hell. It's just math stuff. I mean, to me, this is what a computer's for. But if you're asked to do that, you won't be asked to do something like this on the test. But, I mean, it's possible the AP exam could bring it up. I'm not going to, because most of you guys will get tripped up on doing the stupid math, which bugs me a little bit, but I'm not, it's not a deal breaker. But I'm going to finish because you should be able to do this. It's a binomial expansion. So you square the first number, 4. You multiply the two things together. 2 times 3 is 6. Double it is 12. So minus 12 V2. And then you square the last term, plus 9 V2 squared. So that's a binomial expansion. And then I still have my plus 3 V2 squared. We good? They're on both sides. I'll get rid of those. And I have 0 equals 9 plus 3 is 12. So 12 V2 squared minus 12 V2. Factor out a 12 V2. And I get V2 minus 1. So, I'm just doing your algebra longhand for you because I know some of you can't do it. But that just means that I have two answers. I have V2 equals 12 and V2 minus 1, I have V2 equals 0 and V2 minus 1 equals 0. So there's two answers for V2. 0 is a legitimate answer and 1 is a legitimate answer. Which one of these is the right answer? They both are. It's not a surprise, but you will probably be surprised. How fast was the second ball going before the collision? 0. One of the answers is your original velocity. You're going to get two solutions because both objects had two different velocities. So you get both answers. We don't really want that answer because we already knew the ball started with no velocity. We want the second answer. After the collision, the velocity of V2 is 1. So that's the answer for the first ball. You need the answer for the second ball as well. To get the second ball, I go back to the equation I used earlier. This one. V1 equals 2 minus 3 V2. V1 equals 2 minus 3 times 1. Pretty sure that's just negative 1. So the first ball bounces backwards to the left based on my drawing. The second ball keeps going forwards at 1 meters per second. Again, the physics was here when you interpret the word elastic and know what to do with it. And I'd argue that there's a little bit of physics here, understanding that getting a negative velocity means it went in the other direction. The rest of all this, math. All right, this is algebra. So, in the scheme of like how many points is this problem worth? 4 points, maybe. 1 point for this, 1 point for that, 1 point for doing algebra, and 1 point for interpreting the answer correctly. I know a lot of you would say that most of the work in this problem was doing the algebra, but that was mindless work. Again, that's why computers exist. Your calculator does this. It's built into the TI. It can solve systems of equations. Try it sometime. Do you guys know that it does that? I mean, it's built right in. You can do it on the graph part. Just put all the numbers on one side and put the y equals on the other and graph the two functions. Wherever they intersect, those are your 2 points. It's really, I mean, the math stuff is the least interesting part, but it's the part that confuses you guys the most, I think. But, I mean, I'm not trying to harp on you. I'm just saying that a lot of you get scared away from the mathy stuff, but the mathy stuff is the least interesting thing here. Except for you mathletes. You mathletes love it. Go mu alpha theta. I support school functions. All right, next. Yes, sir.
Go over number 9.
The we in that statement is hilarious. Sure, we can. Being that I'm not pregnant, I'm expecting a lot of help now. Could you read it for me, nice and loud, because I'm old and far away?
A 30-kilogram boy is standing at the edge of a thin, 20-meter-long, 60-kilogram sheet of ice, resting still on the lake. He begins running toward the other end of the ice sheet at 3 meters per second. How fast will the ice sheet move when the boy runs? And what
All right.
is the net momentum of the system?
All right, so ice sheet. I guess I'm not sure how to draw it. Let's draw it from the side. So the kid is standing here, and then the system is at rest before he begins to run. Is that right? So the momentum of the system is 0 because everything's at rest before he starts to run. I think the assumption here is that the sheet has no friction between it and the surface it's resting on. I think that's the implication, like he's running on ice and it's on the water. So he's going to start running this way. That means for the momentum of the system to stay 0, the sheet's going to have to go that way. So what is the mass of the kid? 30 kilograms. All right, so he's 30 kilograms. And how fast does he run?
3 meters per second.
3.
3 meters per second. Yeah.
And how heavy is the ice sheet? 60. Well, it's some thin ice. So hope he survives. So he starts running. The momentum of the system beforehand is 0. The sheet's not moving and the kid's not moving. So this is before the momentum. I'm making this way positive. After he starts running, he has momentum of 30 times 3. So the sheet of ice is going to have to start moving so that the net momentum of the system remains 0. That's it. That's the problem. That's going to be 0 equals, let's just cancel a 30 and make that 2. So 3 plus 2v. So v is going to be -3/2 meters per second, which means the sheet moves to the left or in the opposite direction of the boy. Yes, sir.
What's the collision?
There's no collision. Nothing collides with anything, but there's a change in the state of the problem. And that would be the collision. The kid was at rest, and then he suddenly starts moving. So this doesn't match the profile of how we talked about a collision, but it still matches the profile of a problem where the momentum has to be conserved. So that's still the case. How do you know when one of these things is charging? Is there a way to know? Shit. I think it's charging. I think it was charging before, but I can never tell. I can't believe they used such a stupid plug on it. Nobody has that plug. I don't know what 10 is.
A kid at the Farnell cafeteria wants to propel an empty milk carton along the lunch table by hitting it with a three-game spitball. If he wants the speed of the 20-gram carton, just the spitball hits it to be 0.3 meters per second. At what speed should this spitball hit the carton? Assuming the spitball sticks to the carton.
Carton of milk, spitball, and so a splat occurs, and so now I have a carton of milk, spitball, and it's moving at 0.3 meters per second. That's what I want. All right. I assume they gave us massive spitball and massive milk carton. So can I get those? I mean, this is not that interesting. So we already kind of did this problem, but it's just going to be the mass of the spitball times its velocity plus 0 because the carton's not moving. That's the before momentum. After, it's going to be the combined mass of the spitball and the carton. This is a perfectly inelastic collision because the spitball sticks to the carton and their velocity of 0.3 meters per second. Let's find the mass of you're looking for the velocity of the spitball, right? Do I have to do any more than that?
No, you're good.
All right. Cool. Coolio. Next. I don't know what it is, but
A cart on a frictionless track has a mass of 0.5 kilograms and is up against another cart of mass 0.25 kilograms. A spring pushes the cart apart, and the 0.5 cart has a speed of 1.5 meters per second. What is the speed of the other cart? What was the energy stored in the spring? If instead of knowing the speed of one of the cars and you knew the energy in the spring, could you use that to figure out the speed of each car?
all right. So I guess I don't know if I want to write too much. What is the momentum of the system before you release the spring? Yeah, it's 0. It's not that big a deal. I'm just trying to see if we can all say that. So before you release the spring, they're just sitting there, right? And then after you release the spring, one cart goes one way, one cart goes the other. So something like that. So this is our before and after. So the momentum of our system is 0 still. It's the same as the other problem with the kid on the ice. You release the spring, and we did this in the lab, right? This is when you were hitting the cars and releasing the spring and the cars separated. So we were told the mass of both cars. I don't remember what they are. I know you said the numbers.
0.5 and 0.25 kilograms.
And you got the velocity of one of them, right?
The 0.5 cart is moving at 1.5 meters per second.
All right. So I think you guys see pretty quickly that this only has one unknown. So I get my 0.5 times 1.5 plus 0.25 V. I'm going to make to the right positive again, so that makes my 1.5 negative. Because it's going to the left. Be mindful of direction. And you guys can solve that for V. Pretty sure V is going to come out to be 3. Right, it's a ratio here, so V ends up being 3 meters per second. You want to find out how much energy was in the spring. Now, this part's, I think, kind of important. The energy in the spring had to be the energy of the cars after the spring was released. The energy went somewhere. It went into pushing the cars. So if you want the energy in the spring, the potential energy that the spring had, so this was elastic potential energy, normally we would say that that'd be 1/2 kx squared, but we don't know anything about the spring. Well, this was a conservation of energy problem too. The spring energy became the energy of the carts. 1/2 mv squared plus 1/2 mv squared. Now you have both velocities of the car. So you can pretty easily calculate out the energy that was in the spring before it was released, because it had to be the kinetic energy in the cars after it was released. Now this is going to give you a number. So 1/2 times 0.5 times 1.5 squared plus 1/2 times 0.25 times 3 squared. Now, this will be the energy that was stored in the spring before the spring was released. Now, that last question, that's where the big points come from. This, to me, this would be a 7-point FRQ on the exam. 3 points for getting these two questions right. Probably 2 points here for knowing how to deal with the direction of the momentum and dealing with conservation of momentum, and 1 point for adding together the energy. There'll be 4 points for your explanation that comes from answering the last question. So although you'll think that I'm not going to spend as much time on it, and I'm not, but that's where all the points are going to be. Can you adequately explain whether knowing the energy would be sufficient if you didn't know either velocity? And the short answer is no, it's not enough. If all you knew was the energy, could you determine what the individual velocities were? Now, I think I could probably do it, but I'm not sure you could. But what you have to do is explain if it's possible. So here's what I want you to think. This is what you know. If you did not know either velocity of the car, what information would you have known? Well, you know the momentum of the system was 0, and that the first car would have one velocity, and the second car would have another velocity. You would know that. Could you use that alone to figure out either velocity? Can you solve one of those for V1 and get the number? You think so, Jack? Because I don't know if you can. If you didn't know either of these velocities, I don't know if you can solve it and find just one by itself. But if we knew the energy in the spring, if we knew how much energy was there, we could set that equal to this. Would that be enough information by itself, just this, to determine either velocity? No, it's still just one equation and two unknowns. But together, if you knew the energy in the spring and the momentum before the spring was released, you could probably do it. It would be like doing an elastic collision problem, because you would know the amount of energy in the system, and therefore you could probably do substitution to figure it out. Now, I'm not sure you guys would know how to do that, but now you should. If you know the energy that both cars have, and you know the momentum, you can figure out and predict their individual velocities. All right.
100 miles per hour, or 45 meters per second. A professional baseball
All right, the first part of the problem has the ball coming in,
player solid strike
and then the bat strikes it,
ball with an exit speed of
and then the ball leaves.
100 miles per hour, or
Right? That's the first part of the problem. We could use that to figure out the change in momentum.
The ball could stay
And they go further and tell us how long the ball's in contact with the bat, so we can figure out the force. So this will be a MV final minus M. I think this is a solid question. Equals. I think it's force times time. I know. I don't know any of these numbers. You were saying them. Take a minute. I was busy thinking around with my equipment to get it to work. But before I even bother to try and answer your question or do any more of the problem, pick a direction that's positive. I'm going to pick that direction as the positive direction. I'm going to make the initial velocity of the ball the negative direction. This is the initial velocity. This is the final velocity.
This problem is
Now, I don't
long.
really.
You
So
have to figure out
right now you can
how
solve
much
this for the
the
force.
bat exerts.
Right? You have every other number there, don't you? Mass of the ball, initial velocity of the ball, final velocity of the ball, and the time they're in contact.
So
You have all of it. impulse and change in momentum question. All right? So there's a lot to do here because you need to get all the way to the point where you know how much force is applied to the
Just talks about
to the ball.
12%.
and then you have to redo the problem. So you don't have the
But by
time that's in
increasing the
contact. Time by 12%. Well,
So,
assuming that
can
this
it be
works,
solved then
uh,
for
reboot allows me to connect. You know the time is going to increase by 12%. Mr. Shelton, did you write a bad problem? All right. So the first part of the problem, I don't think you can get the answer.
As the ball coming in
without knowing the initial time that the ball is in
hold on.
contact with the bat. Actually, you could, but it would be pretty. I would not expect you to be able to do it. So, I think you will need a time to do it. And not that I want to belabor it, but you could because T becomes 1.12 times T. That's 12% more. I don't know, do you guys know that that's true? If you know that that's true, then you know that the second case is going to be F times 1.12 T. And that's got to be M V final minus M V initial. This stays the same, and this ends up being 1.12 times FT, which you get right here. So you could do it, but I think that's expecting a lot from you guys. And I'm not sure I would have expected that from you guys. But it could be done without knowing the time of contact. So give yourself a time of contact. Let's say, it's ball in contact with a bat is measured in milliseconds, probably tens of milliseconds. So let's go with 30 milliseconds. So the time of contact would be 0.3 seconds. If you do that, that will make this an easier problem for you. So it can be done without it, but I would not have expected you guys to figure that part out. So there. If you want, I will continue to work the problem, but if giving you the time is enough, then I'll bid that one adieu and move on to the next one.
Yeah, that's it.
All right. You guys do? Was it terrible? Yes, sir.
I just kind of want to know how you word your answer.
I think that's probably a good question to ask. So give me a minute. You will have to say somewhere in your paragraph that the arrow and pumpkin have the same change in momentum. You'll have to also say in your paragraph that the angle the pumpkin makes depends on how fast the pumpkin is going after the collision. Greater the angle means greater the velocity. If you don't expressly state that, I think you're going to lose a point. You'd be referencing conservation of energy. Again, the maximum angle the pumpkin makes is directly related to how fast the pumpkin is going. That's conservation of energy. So what you have to determine then is which scenario does the pumpkin have the greater change in momentum, and that's when the arrow has the greatest change in momentum. Well, when it passes through, that's the least change in momentum, right? It passed through. Its velocity didn't change very much. When it bounces back, that's the greatest change in momentum. The pumpkin stopped the arrow, turned it around, and sent it backwards. So if you have to rank these, bounce back is going to be the greatest. Pass through is going to be the least. Embedded is going to be in the middle. But if you don't mention conservation of energy and conservation of momentum and explain why the pumpkin gains momentum, you can't get any of the points. All right, folks. I will be posting a practice test today. I just talked about this one in first period. So if you have a question about this one, it's up now. I could talk about it again. Sure. I have it, actually. Is it this one we're talking about? Yeah. I went and popped it in here. This is obviously from College Board. I'm not trying to hide that fact clearly, but I want you to understand that this is, I think, very clearly aimed at preparing you for the AP exam. This looks like a 7-point FRQ that has a question at the front where you have to rank something and then explain it. The general form of these is pretty traditional for the exam. You're going to get 1 point and only 1 point for ranking them correctly, and then 6 points for your paragraph. So that tells you right away what they're really interested in. And your paragraph has to hit some important points here. You can get this portion wrong, the ranking, and still acquire some points from your paragraph as long as your paragraph has points that are clearly articulated and represent physics that's appropriate to the problem. But the balance of the points comes from your paragraph. Yes, ma'am?
Will they normally give you like the amount of points that something's worth, or,
They will tell you at the start of the problem whether it's a 12-point problem or a 7-point problem.
but they won't tell you the distribution?
No,
of points? Okay.
you never know the distribution. That's what this semester is largely about. How do we take all of that knowledge and start making it how we get points? This problem has no math in it at all, right? And meaning no calculation. Yet it's full of information that's related to the calculations we've already made. Part of doing all the math is to give you a head for the numbers, but also it's to give you an idea of how it works. If you've been paying attention, and I'm always concerned you're not really paying attention. You get the problem done, you move on to the next one. Do you look at what made that a bigger number or a smaller number? I'm saying that specifically to one like, but to me, this FRQ is about a lot of things. Whatever happens, they're talking about the pumpkin making some angle after the arrow collides with it. You'll need to address the relationship between the speed of the pumpkin and the angle it makes. Is that in your paragraph? If you never mention that, you're not getting all the points. In fact, looking at the way the answer should be written, there's probably several things you have to connect together, not just explain when it comes to the angles here. You tend to think that you just explain those why the angles are. There's a lot. There's conservation of energy. That's what is the relationship between the speed of the pumpkin and the angle it makes. If the pumpkin is going faster, it has more kinetic energy and it will swing higher, converting that energy into potential energy. You'll need to explain that connection. So although there's momentum in this problem, there's also conservation of energy in the problem. Did you make that explanation? Did you explain how the angle is related to the velocity of the pumpkin? I'd argue that's probably 1 to 2 points. Next, and I think this is important, you need to explain the relationship between the speed of the arrow, its recoil, and the speed of the pumpkin. Did you talk about that the impulse experienced by the arrow will be equal and opposite to the impulse experienced by the pumpkin? All right, this is a collision. So in your paragraph, did you mention something about the impulse experienced by the arrow is equal to the impulse experienced by the pumpkin? I think that's the first thing. There should be an impulse argument to equate change the momentum of the arrow to change the momentum of the pumpkin. And I think it'd be best, if you want to ensure the points, that you invoke Newton's third law there. That's why they're equal and opposite. Saying they're equal and opposite probably gets you the points, but if you want to make darn sure you get the points, the reason is because of Newton's third law. The second thing, I already said, there should be a conservation of energy discussion to equate the angle with the velocity of the pumpkin. A faster pumpkin means a greater angle. I don't know that this is necessary, but some of you probably put something in there about momentum is mass times velocity, because that might show up, but I'm not sure if that's necessary. I think it's clear that things with bigger momentum, especially in this case with the arrow with the bigger momentum is one with the bigger velocity. The last thing, you need to now explain in which of these circumstances was a change in momentum of the arrow greatest and least. In which case was the velocity of the arrow changed the least? Well, that would be the pass-through. That's where it was changed the least. right? It passed right through the pumpkin. Its velocity did not change very much. That's the smallest change in momentum. And then there's one where it bounces off. That arrow was stopped, turned around, and sent back. That's the biggest change in momentum. That suggests then that bounce is going to be the biggest arrow for the biggest angle for the pumpkin. And pass through, smallest angle for the pumpkin. That leaves embedded somewhere in the middle. So I think to get all the points, you needed all those three things, and the fourth thing is to explain the change in momentum of the arrow. I think it's incredibly hard to get all the points on these FRQs. Why do you think whenever I show you these FRQ answers, they have like a 2.5 or something like that at the bottom? That 2.5 is the number of points out of 7 that the average student earned on that FRQ. Students do not get very many points in the FRQs. Why the pass rate in this is like 50% nationwide. People don't write well. They don't connect all the dots. You guys, I want you to connect all the dots. Every FRQ is going to have multiple things in the class that you have to bring to bear. No poster is going to help. Maybe we should make posters about the problem like this. That would be good. We could do that. We could make the arrow poster question with the pumpkin. Get orange crayons for everybody, a little green. All right. Just being snarky.
From 2 meters and rebounds from the ground only 1.5 meters.
All right, so this is what you should be able to do on the test. This is the good stuff. This is what I expect. This problem has all the things in it. It's a great question. You start by dropping a ball that is dropped 2 meters above the ground. It hits the ground and bounces upwards 1.5 meters. And you're asked to figure out the impulse experienced by the ball when it was on the ground. Can tell you right now that the ball didn't go as high as it was dropped, right? So we know it lost some energy in this collision. It collided with the earth, but I don't think the earth recoiled very much, right? This is a collision. So we really wouldn't be able to measure the earth's recoil from this, but the earth had an equal and opposite impulse. I'm sure of it. It's just that the earth, it's hard to move the earth. So in this problem, what you have to figure out is that impulse is change in momentum. You're not going to be able to do it with force. You don't know how much force the ground applies to the ball. In fact, I'm pretty sure you're asked to figure that out later. So it's clear that you don't have that information. In fact, that's why I even wrote that part into the problem. So you would know from the very beginning that you don't know how much force is being applied, so you couldn't use force times time. You have to use change in momentum. And that means you have to know MV final minus MV initial. That's what change in momentum is. You don't have any of that. You have the initial height and the final height. But you've been well trained first semester. You should be able to figure out through one or two methods how fast the ball leaves the ground and how fast the ball makes it to the ground. Because you studied kinematics. You could use a motion equation for that. I'm not, because we got something that supersedes motion equations. We have conservation of energy. So I'm going to use conservation of energy because I think that's faster. But you use whatever you want. You have at least 2 methods, maybe 3, to figure out how fast the ball hits the ground and how fast it leaves the ground. So I'm going to use conservation of energy, though. Gravitational potential energy there at the top gets converted directly into kinetic energy just before it reaches the ground. So mgh equals 1/2 mv initial squared. This is the initial velocity. Cancel the m's, solve for initial velocity, and that's going to be the square root of 2gh, where h is 2. I'm not going to do that work again. It has gravitational potential energy here, and it has kinetic energy here. It just has less kinetic energy because it doesn't go as high. But the initial velocity and final velocity will share the fact that they're going to be 2gh, but this time it's 1.5. Now again, you could use a motion equation. You'd probably use v final squared minus v initial squared equals 2a delta x. That would probably do it. It gives you the same thing. So that will get you the initial velocity. That'll get you the final velocity. A different problem tells you the mass of the tennis ball, I think, because they say it's a tennis ball. Now, here's the thing. Be careful. I've left something out on purpose. And it's all around you, but it's one of those things that you just don't think about, and you should. No, actually, but gravity is all around us. But I mean, it's all around this problem. You always forget that these are plus or minus. You always forget that. You shouldn't. Because the ball is going downwards when it hits the ground, then going upwards when it recoils. Did you remember that in this problem you should set a direction to call positive? What direction do you think should be positive? Doesn't matter, pick one. If up is positive, then my initial velocity needs to be selected as being negative. And my final velocity will need to be selected as being positive. This is going to make a big difference in your answer because the ground has to do a lot to get the ball to recoil. It has to stop the ball, turn it around, and push it back upwards. If you don't recall that or do that, you won't get the right answer for change in momentum. So the number part's the least interesting part of this. If you want, I'll put numbers in there. All right, so back to this. I did not record any of that little event of me making fun of Mr. Leota's poster day, but I did record saying that, so it will be on the video. So yeah, Mr. Leota's poster day, somewhere around 45 minutes into this video. Stupid video. I hate these videos. I think I'm done posting the videos too. Yeah, I really am. All right, so are we done with this one? Is there more? I think we have everything you need to do this part of the problem. Is that true? All right, so the next part, you just set that equal to force times time to get the force in a tennis ball. That's it. It's pretty easy. All right, well, that was this one. You recognize that the impulse is bigger because one of the velocities is made negative, right? That's right here, in this portion right here. Because this velocity is negative, you add that momentum. You don't subtract it, making the change in momentum bigger. It is harder to turn something around and send it back than it is to just stop it. That's what this FRQ is largely getting at. And pointless. Next. Yes, Migo, what do you want? Number one? You didn't make it past number one? All right. No worries. But Migo, with your deep voice, you're going to have to really project from the diaphragm, so I don't have a copy of it. So,
Golf ball is contact with the club for only 1/200th of a second. If the 45.9 gram ball leaves the ground at 200 miles per hour, 90 meters per second, what is the impulse imparted to the golf ball, and how much force was applied to the ball from the club? What was the impulse?
you put everything in kilograms, meters, and seconds. The initial momentum of the ball is 0. So the final momentum of the ball is going to be whatever this product is. So mv final minus m times 0 is going to be the change in momentum of the ball. Good so far? And the club, which is going to be the thing that's striking the ball, must experience an equal and opposite change in momentum. So whatever answer you get here, the opposite of that answer, the negative of that answer, is the change in momentum of the club. Has to be. And if you want the force, they tell you how long it's in contact, so it's the same problem there. Just set it equal to force times time. Do you need me to drop the numbers in, or is that sufficient? Yes, drop the numbers in. I'm not pushing the buttons. 0.131? 0.13. 4.131 kilograms, meters per second, or Newton seconds, either of those. Yeah. Oh, wait, never mind. Good. I don't want to mind. And you still have to set this equal to force times time. What was the time of contact?
Whatever,
1/200th of a second? Okay. It's that simple. So solve for force by multiplying both sides by 200. I'm good with that. That's it. That's the problem. Next. Yes, ma'am.
Could we go over the FRQ part